So this is a small introduction to our laboratory called Rapid Manufacturing Laboratory. In fact, today we call it as Hybrid Manufacturing Laboratory. So in this lab, we have two major areas of research activities. One is hybrid manufacturing. By hybrid, we are actually referring to combining competing technologies to work in a complementing manner. So initially we started with combining machining and additive manufacturing. Subsequently, we went for different levels of hybridization. We have at least 5 levels of hybridization. I'll quickly touch upon, but not too much. The second area for interest is large drones. We are not talking about small drones. We are talking about small drone which can be as big as an ambulance. It should be able to carry an emergency patient from the terrace of his house along with a nurse and the pilot, and they should be able to drop him or her at the terrace of the hospital for immediate assistance. That is the noble cause towards which we are working. And I come back once again to hybrid manufacturing. We have been developing machines. We are more into developing machines. Typically, each of my PhD students, he or she has to develop a complete working machine. Maybe it may be up to TRL. You know what is TRL, technology readiness level. It may be up to 5 or 6. Then only they are able to graduate. So we have dealt with different materials in terms of their composition and form. We have used water as the raw material, produced ice as the 3D printed geometry. We have used sand as a raw material. We have produced sand mold out of that. We have used paper sheet as the thank you very much. Paper sheet as the raw material, and we have produced very strong components which are as strong as plywood. And we have also been working on metals. We have used wire, we have used powder, and we are also using sheet form of the metal. And we are also currently working on playing with the composition of the material at different places. Whenever we take a component, it is homogeneous throughout. We are talking today about heterogeneous objects. Typical example of heterogeneous object is our composites. Composites have the fiber in the middle. That is one typical heterogeneous object. But we are also talking about object which will be magnetic at one end and non-magnetic at the other end. It may be aluminum at one end and it may end up with stainless steel at the other end. Things like that, where the composition itself varies throughout the object. So we have a machine which uses a multi-wire system to achieve that. I'm just dumping some information. It will make sense later, if not at the end of the lecture. After some time, you may recall and then you may be able to contact. In terms of kinematics, typically a 3D printer requires only 2.5 axes, because you typically move in XY plane to realize the layer and then move down by one layer thickness to get ready for the next layer. So typically we need only 2.5 axis machine, but we have gone up to 5 axis, 5 degrees of freedom machines, because by using 5 axis, it is possible to eliminate the need for support structure. You may be aware that every 3D printer needs to have a support structure. So we are able to avoid that by going for 5 axis machining. And recently a student developed this 5 axis motion using wire robotics. We also have a traditional 5 axis machine with serial kinematics, whereas wire robotics is a parallel kinematic system. In terms of energies for additive manufacturing, we started with the arc. In arc, we have at least two types, MIG and TIG. So we started with MIG, we went for TIG, and we also bought a laser of something like 4 kilowatt in power. So we have been using it for additive manufacturing. For the last 6 years, we have been working on electron beam for additive manufacturing, and that is the main focus of today's lecture. It's also possible to use resistance heating, induction heating, microwave heating, and all that, but we have not done it yet. We have used induction heating for preheating, but not for realizing the layer. Coming to the drones, we are not talking about toy-like drones. In fact, we are the people to introduce drone in the country way back in 2006. Subsequently, we were focusing on large drones, manned drone, which can be used for drone ambulance. I will play a few videos subsequently. So, in terms of our research approach, any imported product, we can bring down its price to a tenth by indigenization and innovation. That is the promise I give to all our funding agencies, and we have achieved it in many cases. And these three keywords define our research approach: hybrid, discrete, and adaptive. And as already Madam told, we say we will dare with care, because you need to dare when you want to make highly disruptive things. So we do it carefully, but we dare to do it, and we dare to question everything. I'll play a short video of the drone we have developed. This is our drone. You see a lot of innovation. It uses football as the landing gear. It uses 8 rotors of 1 meter diameter. I'm the pilot in it because I don't allow my students to take the risk. I was able to go beyond the 10 meters of height. So the same thing, I want to scale it up to ambulance, which will be a, three-seater. And you'll see that our structure is very simple. We made it out of stainless steel tubes. It is still light enough. Then we also developed another drone which has 4 additional rotors. Instead of 8, we added 4 more to increase its capacity. So that also successfully was flying. So we are seriously, exploring developing ambulance, which required a lot of money. So we are running around. We are talking to funding agencies for the required funding. This is the ambulance I want to develop. It will be about 1.8 meter in diameter each rotor, and it will occupy a space of about 4.5 meter by 4.5 meter. It is available in any terrace. The reason for proposing to use terrace is a lot of dust gets generated when the 8 rotors rotate, and that dust is very harmful for the people sitting in as well as the motor. So we prefer terrace, which is nicely swept and kept clean. Same in the hospital also. Second problem is the nuisance of the onlookers. Whenever something happens, you will find a lot of people coming and crowding the place. So by operating from terrace, we'll avoid that also. So this is how we are planning. From the terrace, we'll load the patient, and then nurse will have the required first aid equipment, and she will care while the pilot will fly the whole thing to the hospital. Okay, I'll come back to now the other area, which is the hybrid manufacturing area. I think already people would have talked about it. So I'll use 2 slides to introduce additive manufacturing. And this is the story you are all familiar with. In the school, they tell us, after telling this story, stay together so that you can fight the enemy. But with respect to additive manufacturing, the moral I will propose is for the lion. Okay, what does a lion do with the help of the fox, it divides the cows, it makes them fight among themselves, and then kills one after the other. So that is called divide and conquer. And interestingly, this strategy is used in many aspects of life, whether it is engineering or whether it is any other problem solving. People have been using it. For example, if you look at the screen itself, this screen has been divided into several pixels, and then we play with the color of the pixels in order to achieve whatever shape we want to display on it. Similarly, finite element analysis, that is also an approach where we divide a complex geometry into known geometries with known equations. Then we analyze the individual cells, collect all the results in the form of a matrix, and then we obtain the various graphs like deflection graph or stress graph. Everything is superposed on the component geometry. That's again a divide and conquer approach. So in the case of additive manufacturing, the divide and conquer approach is nothing but slicing. Now you have a complex geometry here, and that is divided by several planes. And what you see in the figure D, it is the approximate representation of the object we want to build. So by doing it, we have actually degenerated and simplified a three-dimensional problem into several two-dimensional problems, which becomes easier to realize. You can do simple thing like printing the profile on a sheet of paper and then cut with scissors and then glue it one over the other. Like that, you can do many things. So ultimately, what you get is the part shown in E. Okay, what you want is A, but what you get is E, and you can see the difference that wherever the surface is not vertical or horizontal, it will suffer what is called stair step error. Okay, so first principle of additive manufacturing is divide and conquer, and that divide and conquer approach uh, makes it an approximate geometry. So if you want it to be much better, then you can go for thinner and thinner layer thickness, or you can go for some post-processing operation where you finish it to a better finish. Okay, so first principle led to stair step error. The other principle of additive manufacturing is the support mechanism. Support mechanism is required wherever you have undercuts or overhanging features as it is shown in T. On the left side, I have shown the water tank as it is being constructed. So till the cylindrical area is built, you don't have much problem. But the moment it becomes overhanging on the conical container, then you have to put a lot of scaffolds or tubes or plates. After that, you put concrete and then create the conical area. This is nothing but the support mechanism and support structure in the case of construction industry. Similar thing we need for additive manufacturing. So you should note the type of support mechanism and the support structure used in every one of the additive manufacturing processes, because this too influences the surface finish. For example, you see this T geometry that when the overhanging feature is built, they would put a lot of triangular support structures as it is seen in the water tank. At the end of building it, you have to cut it off. Okay, when you cut it off, you are doing it manually. So when you do it manually, you may cut little more into the body, or you may leave the support a little bit. So that results in a rough surface finish. So wherever you remove support, there also you lose your surface finish. So the conclusion is there are two principles in additive manufacturing. One is divide and conquer or slicing approach. The second is a support mechanism. And both of them lead to a surface finish problem. The first one leads to a surface finish problem called stair-step error. Second one leads to support removal. When you remove the support at the interface, you get a rough surface. Furthermore, you also lose material because whatever you cut away, you throw it. It's not reused. So that is another wastage. So these are the two principles which also give rise to two surface finish problems. So this is a simple introduction about additive manufacturing. And this slide captures the various capabilities of this young technology. The first 3D printer was introduced commercially in 1987 by 3D Systems, and the equipment was called SLA, Stereo Lithography Apparatus. Okay. Since then, it has been influencing in a big way. So 1987 to now, it is about 30 years of 3 decades, you can say, or little more than 3 decades. But it has influenced the manufacturing industry and the product development industry in a big way because additive manufacturing is more automatic than a CNC machine or a robot, because you don't do process planning. You only give the CAD model and then it produces the part automatically. It does slicing, it does support structure building, it dispenses material. Finally, it gives you the object. So we call this machine as a totally automatic machine. Okay, the level of automation is the highest in additive manufacturing. So it drastically cut down the product development cycle time. But subsequently, people realize that apart from cutting down the product development cycle time, it also has some very interesting geometric and material capabilities. So as you can see, on the left side, I've shown some examples of its geometric capabilities. On the right side, I'm showing its material capabilities. So on the left side, when we look at the geometric capabilities, you can see that the first two examples, these are assemblies. One is a wrench with a moving jaw and fixed jaw with a worm in it. And the other one on the left extreme, top left extreme, is a spear inside a spear inside a spear. So three spears are one inside the other. So in the traditional way, you will make the spears into hemispheres, put one inside the other, and then glue them together. Whereas here, you can build it in a layer by layer in one go. The third figure, it is actually the combustion chamber of the aero engine. Here again, the entire thing in the past used to be manufactured out of sheet metal, a lot of stamped pieces, and a huge welding used to happen. About 50 components used to be welded together after forming them into the desired geometry. Whereas today, from powder, metal powder, you build in layers and then produce it in one go. So while the first two are movable assemblies, the second one is a fixed assembly or welded assembly. So building assemblies directly is a very important capability of additive manufacturing. Second important capability is producing very complicated ducts. For example, you see the bottom left piece where you see two holes. These two holes, it goes downward, join a torus, and then come out. So this is nothing but a cooling channel. So such a cooling channel can be very easily realized using additive manufacturing. I'm not saying that other processes cannot do it, but they will require more efforts to do that, whereas in additive manufacturing it is very simple and elegant. Now look at this Allen screw at the top right on the geometric figures. Allen screw, you'll know that only the thread is taking the load in any screw joint. Okay. So the central area is really not contributing anything. So in this particular Allen screw, you see how much of hollowing has been done. The complete central area, it has been hollowed with six ribs on it. Similarly, on the head also a lot of lightening has been done. So you have space only to put the Allen key. So this way, when you talk about aerospace, you become very sensitive about the weight. So this becomes very important. Although additive manufacturing will be expensive for this application, aerospace can afford because every gram counts. Now, exactly below the screw, you see a bracket. The bracket also is highly lightened. On the cylindrical area, you see honeycomb-like structure. This is difficult by many other processes, whereas additive manufacturing in a layer by layer manner, it can produce. So very light components can be produced. Complicated ducts like this can be produced. Here you see the ear plug. In addition to ear plug, you can also look at the knee joints on the right side. So you can make customized medical implants as well as um, the other elements. You sometimes some fixtures for medical application can be produced. So it has a lot of customized solutions possible. So very complicated geometry is possible. This is on the geometry capability side. On the material capability side, at the bottom left, you see the same knee joint in the form of a SLA part. SLA is stereolithography apparatus. Out of photopolymer, it is built, and you can easily see that it has a lot of hollowness in the form of honeycomb structure. This is used in place of wax pattern, and then uh, mold is produced around it, investment mold. Then it is burnt off, cleaned nicely, and then the required either stainless steel or titanium material is poured, and you get the uh, customized knee implant. So such things are possible. So that means there are two types of heterogeneity. One heterogeneity is presence or absence of the material. Second heterogeneity is the variation of the composition throughout. For example, on the right extreme, you see a titanium component. At the top, the percentage of titanium is only 50%, whereas at the bottom, the percentage of titanium is about 86%. Okay, so the percentage of titanium can be varied all along. So you produce objects which are heterogeneous or gradient in nature. So these things have become possible thanks to additive manufacturing. So a new area is emerging, which is known as DFAM. It's a subset of DFM. You know what is DFM? Design for manufacturing. Okay. So DFM AM is specifically for design for additive manufacturing. So let me once again show the Allen screw, Allen bolt. Here, uh, the threaded part should not be manufactured by additive manufacturing because the threaded part is very fine and it has small triangular thread, and each of the triangular area will be step approximated. So that will become weaker. So normally what people do is they keep additional material for the threaded area and then they go for thread rolling. Okay, so processes have to be combined nicely. Additive manufacturing cannot be used everywhere. It is not an universal solution for everything. So you need to know where you will use thread rolling, where you will use additive manufacturing, where you will divide the components and make it in multiple pieces of AM, or where you will combine them into one part and produce it. So all these are addressed in an area called design for additive manufacturing. It's a very, very active area of research. Some of you may like to jump into this. Similarly, when you talk about heterogeneous objects, again, a very interesting area of research. Now, I'll quickly show some of the hybrid machines we have built. This is one of the largest machines we have built. It has consumed more than 16 crore of funding. This actually captures my 25 years of research in additive manufacturing. And it's a very professional machine. Today, it's available for technology transfer. This machine can do many things. it has gone to the 5 levels of hybridization. In the green window or box, I've mentioned it. We can do material addition and subtraction on this machine. So you see this machine, it has at the left extreme a spindle system along with the ATC. So that's a milling part of it, which takes care of the subtractive manufacturing. It has more than 20 tools available. So you can preset the tool and it can do subtraction. And you see six tool posts. You see the six tool posts. These are moved up and down as a z-axis. Each of the tool posts can have different tools. For example, the first one will have MIG or TIG welding with multi-wire. Second one is our laser system, 4 kilowatt wire. We keep changing. These tool heads are generic. We keep changing. This photograph probably belongs to 2 years ago. Okay, now the third one is our CMT MIG cladding system. You see the on the top right figure CMT written. CMT stands for cold metal transfer. It's a kind of MIG system where metal transfer happens without too much of spatter and very smooth operation. Then you also see look at the top right figure. There's a small hammer with a blue color pipe connected. This is nothing but pneumatic hammer. You know, when you do welding and produce the layer, a lot of stresses get built because of the thermal gradient. So the nature of the stress is tensile. So when you hammer on the welded surface, you nullify the tensile stress and then it becomes a normal component. Sometimes if you want more strength, you can make it instead of tensile, you can hammer more and make it compressive. So then you can produce forging like component. So this is a kind of stress relieving system. And at the right, you see a red colored box. That is our 25 kilowatt preheating system. So you can preheat the previous layer to 500 degrees centigrade or as required. We can go up to 700 degree in this machine. It's a 25 kilowatt heating system, induction heating system. So we preheat the previous layer. After that, we do welding on it. So by doing it, we are able to minimize the possibilities of the residual stresses. Instead of depositing on top of a surface which is at room temperature, you deposit on top of a surface which is at 500 or 550 degree centigrade. As a result, the chances of stresses will be less or the extent of stresses will be less. So this is a very composite machine with several tool heads. It can do material addition and subtraction. It can have at least three different cladding heads, laser, MIG and TIG. And it is a full-fledged 5-axis system. Therefore, we can avoid the support mechanism. That is our third hybridization. So we have 3 axes as well as 5 axes on the same machine. On the same machine, we have laser as well as arc. On the same machine, we can build the part in a horizontal layers or it can be conformal. We are all biological systems are also additively manufactured, but they grow in a conformal manner. They don't grow in a planar horizontal layer. So we are able to produce some components like impeller in a conformal manner. So that is the fourth level of hybridization, which is related to slicing. The fifth level of hybridization relates to material. So on to the electron beam or arc or laser, we have 4 wires going into it. So the energy beam basically creates the molten pool. Into that, the wires will plunge in and melt away. So if we have 4 wires, if we can have different compositions of the wires, then by controlling the wire velocity and as well as the 5 axis motions, so you have totally 9 degrees of freedom, using which you will be able to realize components which have the interior composition as well as porosity varying. So this is a very, very interesting aspect of our system. So we have 5 levels of hybridization. That's why we call it as hybrid manufacturing. Addition and subtraction, combination of different energy sources, combination of different degrees of freedom, combination of different slicing strategies, and combination of different material compositions. So this is a beautiful machine. So if you happen to visit Mumbai, drop in and have a look at the machine. These two are our electron beam systems, and these two are the guys who did PhD in that. So I mean, it's a very tough job for them because we placed order on a company in Ahmedabad, and we hired a house there and put these boys there. In fact, at one time, these two PhD students were living with two other MTech students who were contributing. So they were working in the company and supervising as well as contributing to the development of the machine. The left side machine is for powder bed technology or powder bed fusion technology. The right side machine is for multi-wire cladding based system. It was completely indigenously built by us. The left side student Avinash, now he has become a faculty in BITS in Goa. Right side, he is a postdoctoral fellow with us. He is continuing with us. He wants to give the finishing touch to these machines. Okay, now the left side, we have a machine which can produce thermocol objects. The thermocol is loaded onto this machine in the form of a rectangular block, and using hot wire slicing and an ATC based milling cutter, you will be able to cut and slice thermocol and then glue one over the. So three different tools are used. Two are for subtraction, hot wire cutting or hot wire slicing. Then 6 station ATC milling system or turret based milling system. Finally, after the slice is ready, we glue them together. Now you see this entire part is produced out of just 3 slices. So you can see the kind of layer thickness on it. They are all sometimes as big as 2 inches the layer thickness. It's a beautiful machine. So using the thermocol or foam pattern as pattern similar to investment casting, we can produce metal part. So this foam pattern was made on this machine. Using this foam pattern, we produce this metal casting. This is related to rapid casting. Another machine which uses sand as the raw material, it builds molds like this. And this mold is for producing the casting like this. So this is our sand 3D printer. This is our ice 3D printer. So the first figure here is the ice pattern produced on this machine. Using this ice, using plaster of Paris as the mold material, we produce the mold. And remember, ice is at less than 0 degree centigrade. Okay, so and the slurry, plaster of Paris slurry will be at 15 or 20 degrees centigrade, even if you put it in the refrigerator, pre-cool it. So rather than absorbing the shape from the pattern, it will start giving heat to it and melt it, and the geometry will be ruined. So we adapted a very interesting method called sublimation. You know what is sublimation? From solid state, you can go directly into a gaseous state. From ice, it will become vapor or steam. So that's what we did. This is also known as freeze cooling, because we uh, put the after pouring the slurry, we put the whole thing inside a refrigerator and also apply vacuum on it. See, ultimately the region, whether it is sublimation region or melting region, it depends on the pressure and temperature you apply on it. We did that and we were able to get the mold very nicely reproduced. Then we obtained the metal casting from that. So this was built by a PhD student single-handedly. Today he is a faculty in BITS Pilani. Another student built a FDM-like machine, plastic machine, but he did two great innovations. One innovation is he doesn't use wire or plastic in the form of a wire and then use pinch wheel based drive. Instead, he used granules used in injection molding. You know the injection molding process to produce plastic parts. So he used the same granules which costed less than 1/20th of the price. They cost anywhere from 150 to 200 rupees per kg, whereas if you want to buy the same material in wire form, it will be 20 times more expensive. So he used that, and productivity also is very high because it is the screw used in the injection molding. So that is one innovation he did. Another very interesting thing he did is he used wire robotics, very similar to Katputli. Okay, so I don't know that. I think I have. You see, this is the machine working. It's a hexagonal platform. It's able to deposit the layer the way he wants. So he is now in Germany doing his postdoc. Very productive student. Right from BTech, he did PhD directly. And he was also a PMRF fellow, which means he was getting about 90,000 rupees stipend, 90, and also 2 lakh, I think, contingency money per year. So he already spent uh, 2 1-month visits to Purdue University. Okay. Now, this is another contribution from PhD student. Here, paper is used as the raw material, and a laser is used for cutting as well as gluing, because this paper has a glue on one end. So when we defocus the laser, it will do the joining operation. When we focus the laser, it will do the cutting operation. So this we call as opti-lamp, because we optimally cut the paper so as to minimize the wastage. Okay, so this much about the various projects our group has done. Now I'll get back to uh, electron beam based hybrid manufacturing. It's 16:10, 4:12 now. So I have about an hour. We will till 5 I can go, less than an hour. So we will do justice, not a problem. Okay, so is this in presentation mode? Are you everything okay? One of the organizers can answer, please.
Sir, okay, sir. It's visible, sir.
Yeah, okay. Okay, now we are coming to the actual topic. We call it as electron beam hybrid manufacturing. Here we have two aspects. One. Yeah, this is the PPT. So we call it as electron beam hybrid manufacturing. Hybrid because it has material addition as well as subtraction. Apart from that, it can also do preheating, post heating for stress relieving and things like that. So as I told you, we have two machines. One is for powder bed fusion technology, where the raw material is powder, obviously. The second machine uses a multi-wire. 4 wires feed into the molten pool. I'll show the photographs after the introductory lecture. Okay. So I want to talk a little bit about space, energy, and time. So according to me, the universe has only two things. Okay. I call them as two E's. One E is the vast emptiness, E for empty. Second E is energy. Okay, the vast emptiness or Akash is nothing but Lord Shiva. And the energy is nothing but Shakti. Okay, so ultimately only these two things will be permanent. So the space is infinite in terms, and XYZ are just our method of representing. Otherwise, we are talking about a vast, infinite, empty space. Now, this empty space is filled with energy. Now, energy itself will assume different forms. Okay, so as we are all aware, Einstein's equation E is equal to mc square says that energy and mass or matter are interconvertible. You can convert energy into matter and matter into energy. Okay. So the energy itself can be in again many forms. It can be in heat form, which is the ultimate form. It can be a mechanical force, it can be electrostatic force, it can be magnetic force, and many other forces. Okay, I call heat as ultimate because every other form of energy can be fully converted into heat energy 100%. But heat can never be converted 100% into any other form of energy. That is our, I think, second law of thermodynamics. Am I right? So heat can never be converted into the other form 100%, whereas the other forms can be converted back to heat in 100% efficiency. That is how all these, limitations, theoretical limits like Carnot cycles and all come into picture. Okay, now energy itself can be in many forms of its own. Then energy can become matter. Matter itself, as we all aware, there are three forms of matter: solid, liquid, and gas. And this state of the matter is decided by the pressure and temperature fields acting on the matter. So the matter has the pressure and temperature field acting on it, as a result of which we have phase diagram. I've shown the phase diagram here. Phase diagram for each of the materials. On the x-axis, we have temperature. On the y-axis, we have pressure. And the regions are divided. You can see that left extreme is solid. Then we have liquid. Then we have gases. And they can go from one to the other depending on the temperature and pressure variation. That is how we saw sublimation happening at the earlier ice 3D printing case. Okay, so these are called field. Pressure is a field. Heat is also a field, or temperature is nothing but a measure of heat. So temperature field. So depending on the field value, the matter will be in solid, liquid, or gas form. And these are the three most popular things we are aware of. But subsequently, when we go through physics, we find that there are many more fields like pressure and temperature. Therefore, there are also many other forms of matter, not just three. For example, plasma. Plasma is the ionized state of matter. Okay, that means under the influence of electrostatic force, ionization happens. So you have plasma. So plasma is everywhere. Like that, when I went through Wikipedia, at least 10 states are listed, each connected with a different types of fields. So there could be magnetic field, there could be electrostatic field, and things like that. So we have now five states. Okay, energy is one. Space is another, solid, liquid, and gas. So you can actually combine them with the Pancha Tattvas. So space is nothing but Akash or Lord Shiva. Energy is Shakti or Surya Dev. Then you have earth solid, you have Varun or water available here, and the last is gaseous form or wind. So these are actually coming as the Pancha Tattvas. Therefore, we actually say that whenever somebody dies, he has merged with the nature, because when the body is burnt, it divides into four parts and then combines with the nature. Okay. And sometimes we also say that he has become a point in time, because in the entire scale of time, we become a small point. So we say he has become a point in time. The equal words in Tamil, I can say, it may be there in other languages also. When we say he has become five elements, we say இயற்கை எய்தினார். And then we say காலமானார். Okay, kalam refers to kal. Kal is time. And in a way, they say time is actually black in color. Okay, it's like that. A lot of it's a combination of science and mythology that I've been talking about. Now, I am also tempted to think that I hope I'm not going too much away from our discussions. So, apart from energy and matter, energy can also become time. Energy can become memory. Energy can become life, and there could be many other forms of it which are not easily understood by us. So this is a slide I thought I should share with you, explaining the scientific and mythological details. Now I'm coming back to science again. So there are three forms of energy I was talking about for additive manufacturing. One is arc. This is in the order of me starting. Okay, I didn't have too much of money. With 5 lakh, I could buy a MIG welding system. So that is how I started additive manufacturing. So MIG or arc-based energy is one form. Then the laser-based energy is the other form. Okay, uh, when the electrons go left and right on both sides, left side you have an opaque mirror, on the right side you have a semi-transparent mirror. So after some left and right iterations, it accumulates sufficient energy and velocity and it gets out of it. Okay, and then it comes out as the laser beam. Okay, so you have a coil which gives the excitation energy for it to sustain the zigzag motion till it comes out of it. So that is a laser. And in arc, what we are doing is we are ionizing the space. We apply a voltage, we ionize the space between them, and then when there is also voltage difference between them, they come to the target and bombard with high velocity. So you get the energy transfer or melting happening. So that is arc. Now this electron beam, we have seen olden days TVs, that's called CRT or picture tube, cathode ray tube. In fact, in the past, they called electron beam as cathode ray. That is how the word CRT came. But subsequently, we prefer to call it as electron beam because cathode ray is nothing but electrons, collections of electrons. There's no other particle. So electron beam is the more apt word. So this picture tube, you just turn it 90 degrees. That is nothing but the electron beam welding system or electron beam hybrid manufacturing system or electron beam additive manufacturing system. Okay. So if you look at the fundamentals, in the case of laser, electrical energy is converted into photon or light energy. Okay. I told you already, when energies are converted from one form to the other, if the terminal form or the target form is heat, 100% is possible. Otherwise, any other conversion cannot be 100% efficient. That is why you find that lasers take electric energy and then you produce optical energy. So it is not more than 15 to 20% on a continuous basis. There are situations where people have demonstrated 50% conversion, 50, but that is not in all places. That is in ideal conditions. So that explains why laser is inefficient. Okay, but it is very sharp. When I say inefficiency in terms of energy efficiency, otherwise in terms of process efficiency, laser is extremely uh, diverse and versatile. Now let us compare. So let us leave away laser. That is not the topic of discussions now. Let us compare only arc and electron beam system. Now they differ only in terms of the voltages and current. See, the arc machines, we have a machine which can go up to 400 amperes and its voltage may be less than 160 or 120 volt. Okay. So you can say that arc is a system. Both are electrical systems. Okay. And both are electrical and they finally convert the energy into heat form. As a result, the conversion efficiency approaches 100%. Easily, you get arc machines and EV machines for 95% energy efficiency on routine basis, not at special cases. But they differ only in terms of the voltage and current. So, whereas the voltage here is of the order of 150, sometimes for fine welding, we go up to 20 volt also. Okay, current can be up to 20 amperes. Otherwise, there are situations where electroslag welding and all, they've gone up to 1000 amperes easily. Okay, so this is a system which is low voltage, high current. On the other hand, electron beam is a system which is high voltage and low current. Okay, this is the basic difference. Low voltage, high current, high voltage, low current. And I told you the values of this. In this case, we minimum use 60 kilovolt. 60 kilovolt. Okay. Let's say the wattage is almost the same. Let's say a 4 kilowatt or 12 kilowatt. Okay. When you use this 60 kilovolt, for 4 kilowatt, it will be 66 milliampere. For 12 kilowatt, it will be 200 milliampere. So here we are dealing with kilovolt or thousands of kilovolt and milliampere current. Here it is several tens of voltages, several hundreds of current. So the fineness or interesting applications of both, as well as their cost, come from this major difference. Okay, based on this, we can compare other things. For example, pressure. You need always ionization to take place. For ionization, you need environment. So you need gas. So the pressure of the gas is about 1 atmosphere or a little more because argon will come with some force. So at the arc, the pressure is slightly more than atmospheric. Okay. And the gap between the electrodes is hardly 10 millimeter or 8 millimeter. But when you come to electron beam, you are dealing with 60 kV, 200 kV also is possible. So your currents are less and you can accelerate for long distance. So the gap between the cathode and anode can be as high as 500, even 1000 millimeters. So the gap is very less here. The gap is very high here. Okay. And because the gap is very less, the beam diameter also is very high. So the precision is not very good. Whereas here, you have 700 millimeter, 800 millimeter for the electron to accelerate. So along the path, you can concentrate it or you can focus it. So we are able to get electron beam, which for our kind of applications of 4 kilowatt to 12 kilowatt, we are able to get easily 0.5 millimeter diameter of the beam. Whereas in the arc, it will go to 5 millimeter, 6 millimeter diameter beam. Okay, and same electron beam concept is used in SEM, scanning electron microscope. There, the beam is of the order of microns, 10 microns, 12 microns. And the beam can be deflected onto the sample at something like 1 lakh meter per second. Now think of the magnitudes. In the arc case, the torch speed cannot be more than about a meter or so per minute, meter per minute. Whereas in laser, the scanning speed using galvanometer can be of the order of 100 meter per second. So 1 meter per minute versus 100 meter per second in the case of laser. Whereas in electron beam, for scanning electron microscope, the speed is 1 lakh meter per second. And for our additive hybrid manufacturing applications, it is 10,000 meter per second. So that's a kind of scanning speed we are talking about. That is because in the case of arc, the movement of torch is by the mechanical movement of the table or something like that. So you use regular motors for it. In the case of laser, you have a galvanometer which has very fine few grams of mirror oscillating. Whereas here you use coils. Okay, you use coil or some kind of electrostatic force to deflect the beam. So there's absolutely no inertia. Okay, so it's not just the velocity, it is the acceleration which is also important. In the case of arc, your acceleration will be 0.5 meter per second square. In the case of laser, it can go up to 8,000 meter per second square. Whereas here it is close to infinity because velocity itself is 1 lakh meter per second. So acceleration will be much higher than that. So that is making it attractive. But then there's a huge negative side. You cannot have electron beam moving in atmosphere because then the electrons will start interfering with the gaseous molecules in the atmosphere and then they will never reach the target. So electron beam has to be inside a vacuum. Vacuum means extremely high vacuum, 10 power minus 6 millibar. It's extremely high vacuum. There is hardly any atom inside. That's a kind of vacuum we are talking about. So electron beam gives us three challenges which start with first letter as V. One challenge is vacuum. The entire thing has to be in vacuum. And another challenge is voltage. 60 kV is minimum. If you and up to 60 kV, you don't get any other radiations. The moment you exceed 60 kV, you get X radiation coming and other radiations coming. So you need to make the wall thick. You have to put lead lined protections and all. So that is related to the voltage. Second is vacuum. When you deal with such a high vacuum, things become extremely difficult because we have to send inside the vacuum both energy and mass. Okay, energy in the form of the high voltage. We have to send the energy into it. We have to send at least all the three forms of matter has to go in. We need to send in for the purpose of tool changing pneumatic air inside. That means it cannot be an open loop. You know, when it opens the chuck or closes the chuck, whatever gas it releases, it has to be taken back and then it should come out of the chamber. It cannot be released inside the chamber. So we have to communicate gas and take it out. We have to communicate water, because water is required for cooling system, motor cooling. Because among the three heat transfer modes of conduction, convection, and radiation, convection is simply absent. Radiation is not very effective because your temperature is only the melting temperature. So the radiational effect, which is proportion to the fourth power of temperature, is not very high. So we are depend only on conduction. So convection, in order to get the convection happening, we put cooling jackets on each of the motor and then send water inside to benefit from the convective heat transfer with a combination of conductive heat transfer. So heat transfer becomes a nightmare when you deal with electron beam systems. Because you have to convey three forms of matter. You have to convey energy. Energy also, it goes in different forms. One is the high voltage energy. Then you send energies required for running the motor. Then the motors have encoders. So the encoder energy is in the form of pulses and signals. They are at low voltage, but they cannot be corrupted. So all that has to go through. So this is quite a challenging task. So the three challenges are voltage, vacuum, and velocity. So if you have to deal with 10,000 meter per second motion system, typical CNC controller will fail there. So we need to come up with a combination of analog and digital systems to do the motion control. So this is what we have been enjoying, the three challenges on voltage, vacuum, and velocity. We have been enjoying and learning for the last 7 years. We were lucky to find an expert in Ahmedabad, Dr. Venkat Ramani. He's about 72. So all the team is there, and I visit every week to monitor the progress. Okay, in this slide, I have listed the significant advantages of electron beam. I already told you energy efficiency can be as high as 95% because electric energy becomes heat energy, whereas laser is hardly 15 to 25%. Okay. Then the scanning speeds, we are able to get as high as 10,000 meter per second compared to a laser, which is 10 to 100 meter per second. So this gives it a lot of possibilities. Please don't be under the impression that the productivity increases as compared to laser because your scanning speed is 1,000 times faster. It is not going to lead to productivity increase. Instead, now think of scanning a typical layer in FDM. In FDM, the scanning happens at something like 0.5 meter per minute. Okay. Whereas here it happens at 10,000 meter per second. So it is the scanning happens so fast that it's like a flash, or the entire layer of the object or entire slice gets heated instantly, virtually instantly, because it happens in microseconds. Okay, so instantly, like a flash in a camera, it happens. As a result, uh, the temperature rise is uniform throughout, which means there's no residual stress. So when you go for such high velocity scanning, there is absolutely no residual stress. Okay, that is the most important benefit of going for high scanning speed. It is not really to give higher productivity. The third benefit, initially vacuum was considered as a limitation. Even now it is challenging us a lot, but the community, human community has understood vacuum in a much better way. So we have very efficient vacuum pumps. We are able to realize the vacuum within about 10 to 15 minutes, the complete chamber of 2.1 meter by 4 meter height, we are able to get it. So that is under control. But then when you produce the whole thing in vacuum, absolutely no contamination happening. Because Air molecules are not there. No other molecules are there. Therefore, the part you produce is shiny all the time. That means it is pure. It has two types of versatility. EB is the ideal tool for all sorts of metals. It is not yet available for non-metals like ceramic and plastic or polymer. I put materials into only three forms: polymers, ceramics, and metals. You also have studied about molecular bond. We talk about covalent bond, ionic bond, and metallic bond. So these also correspond to these three classifications: polymer, ceramic, metal. Okay. So electron beam very comfortably handles all types of metals, whether the metal is poor conductor or good conductor, reflective, refractive, it handles very well. Whereas when you talk about laser for highly conductive materials like aluminum, silver, gold, copper, even for copper, it struggles because these materials reflect all the laser energy because optical energy. It reflects most of them and then very little goes into the part. Whereas electron beam comfortably handles copper, gold, every kind of material. It could be refractive material like tantalum, very complicated materials. It can handle with greater ease. That is in terms of material. In terms of operation, the same beam can do preheating, post-heating, melting, cutting, joining. Another very interesting feature which is not possible with any other system is when the voltage used, acceleration voltage is beyond 60 kV, you get X-ray coming out of the molten pool. Okay, when the voltage is high, the electrons get excited and then they start emitting X radiation. This is a negative thing, definitely. But if we take enough masking and protecting the human being around, it is possible to put receptors, X-ray sensors, which will predict the microstructure that will come after the solidification. Accordingly, you can use this to correct the process parameters. So you can predict the microstructure from the X-ray being emanated and you can correct it. This is a very beautiful application of electron beam. In my lifetime, we won't be able to do, but I'm sure a lot of people are already working on. So this is the kind of versatility you get for electron beam. You may ask me, why can't we do preheating and post-heating using laser also? See, in electron beam, uh, you scan the layer very fast. In few milliseconds, you scan the layer. But in few milliseconds, you don't get the required melting temperature because you scan too fast, so you have transferred very little energy. So in electron beam system, we keep on scanning the same thing again and again and again. Because the whole thing is in vacuum, slowly the temperature of the layer rises and then at some point melting takes place. Then we stop the beam, then solidification takes place. Okay. You may wonder why it cannot be done with laser, because lasers can go up to 200 meter per second today, and that speed also keeps on increasing. The reason why we are not able to do is we have a gaseous atmosphere surrounding the component. Therefore, convective heat transfer all the time is happening. So there are some researchers who are looking at using laser inside vacuum. Laser can very much work inside vacuum. Only arc cannot work inside the vacuum, but laser can very much work inside the vacuum. So a time will come where lasers also do very fast scanning, if definitely not comparable to electron beam, but they will also do very fast scanning and reach some nice level. Okay, then other things are minor. So as I told you, these are the three machines we want to develop and two are already developed. These are our powder bed based additive manufacturing system. We built it under a UAV project. It's called Unchatar Avishkar Yojana. Yes, manufacturing systems in Bangalore gave us 25% of the money. That means almost 1.25 crore. Remaining 3.75 came from MHRD. So we built this machine. We initially took technology transfer from BRC Mumbai because BRC was banned from these technologies because it's a strategic organization. So for the last 40, 50 years, the engineers developed the system themselves. So we took technology transfer. Unfortunately, during the pandemic, they were not able to help us, and I was lucky to locate Dr. Ramani. So the subsequent machine we built on our own under his guidance, and we made a lot of interesting changes. You see this chamber, which is more rectangular, and its wall thickness was more than 25 millimeters. We went for cylindrical dome-like chamber. Wall thickness of this size wise it is much bigger. This is 2.2 meter in diameter, whereas this is only 1 meter in length. But in spite of this kind of diameter, the wall thickness we use is only 8 millimeters, and we don't use any rib except one rib here and another rib inside the chamber. Only two ribs were used for strengthening because the hoop stress takes care of all these issues. Okay, so this was a very interesting thing. And in our machine, you will also see that the cut is slant. I'll come to that little later. The cut is slant, and there's no separate door as in the first machine. We don't have any hinged door here. The entire thing, like an eggshell, it will open and close. So this is for powder, this is for multi-wire, and this is for sheet metal, but we don't have any funding. The second machine, we had funding of something like 6 crore. L&T Mumbai gave 25% of the money, and DST gave another balance of that, 3 times that. Okay, so let me once again explain the principle because we have just 15 minutes left. So what we do is called thermionic emission. Any body above 0 Kelvin will emanate electrons. Okay. When its temperature increases, then the amount of electrons emitted will be much higher. That's a very simple concept. So what we do is we have a small tantalum filament. As you see in the bulbs, you have filament. So small tantalum filament, we apply uh, something like 100-watt power. At 2 volt itself, it gets enough energy and 50 ampere current. So within about 100-watt power, it becomes red hot, and then it emanates electrons. So when the electrons come out of it, it is virtually at zero velocity. Okay. Now, then what we do, there is a cathode here. Cathode has a hole. Okay. And this is called, you ignore the grid for the time being. Just think of this as the cathode and this as the anode. The voltage between them is 60 kV. So what will happen? All the electrons will accelerate fast towards the anode, but the anode has a 4 millimeter hole here. So they won't really go to the wall of the anode. Hardly 10% of the electrons will go to the wall. Rest of them escape through the hole. So when they escape through the anode, they reach something like 0.6 C. That means 50 to 60% of the velocity of light is reached by the electron. So they have huge amount of uh, kinetic energy available. So when that goes very fast and hits the target, it creates a molten pool, melts the material. Now in between we have a lot of other things. Electrons, they come and then the anode has 4 millimeter hole. So the beam coming out will also be almost 4 millimeter in diameter. So here we have a coil which focuses it. It's a simple coil creating a magnetic field. Under the influence of magnetic field, all the electrons are pushed towards the center. So focusing happens. And then you also have deflection coils, one pair for X, another pair for Y. So when you put different voltages to this deflection coil, then the electron deflects towards or away from it. By using the deflection coil, you can position the beam anywhere at the scanning rate of something like 10,000 meters per second, because there's no inertia. It's only the current flow you change. There's no inertia. So this is how it works. Now I want to, so now we understand that the filament is the cathode. We have an anode. We have a focusing coil. We have a pair of deflection coils. There are in fact many more coils, but we'll talk about only deflection coils. Then in between there is something called grid. Okay, this grid. So 0 to 60 kV is possible. By applying more negative voltage to the grid, you have the possibility of pushing the electrons back towards the cathode. Because this is how you do the wattage control or power control. Totally, let's say 4 kilowatt or 12 kilowatt is possible. So by controlling this voltage on the grid, you throw back some of the electrons. By that you control it. So power control happens by the grid. Grid also, of course, does inherently some amount of focusing. It does many more things. And in the cathode ray tube, you will find that there are at least 3-4 grids available to make it more cohesive. Okay. Now, we already discussed it. Spherical geometry is the ideal. Cylindrical, horizontal, cylindrical, vertical, box shape, everything is possible. But spherical is the best. And dome-like shape, cylinder with a dome on both ends, that is a compromise between the less space available in sphere and more space available in the rectangular system. In a rectangular system, you see that wall thickness is as much as 30 millimeters, and you need to put a lot of ribs. Okay. So to avoid that, our initial design was rectangular. Subsequently, we went for dome-like geometry. So I move a little faster because we need a few minutes for discussion. So here, this is the machine we built. This is the electron gun. Typically, you'll find that the electron gun is outside, but in the second machine, we put the electron gun inside. And what you see here, a large system, which is like a big factory, that is the system which produces the vacuum. And then in the powder bed system, we have made a table which is like a scissor kinematics. Okay, so after I saw it as a scissor kinematics, and these are all the motion system inside. Typically in all additive manufacturing machines, you will find that they spread powder from one end to the other on a rectangular geometry. But after seeing the circular geometry of the table, I remembered dosa. So we decided to spread like a dosa. So you see on the right side machine, this is our sand 3D printer. We spread it like a dosa. We put the required powder in the middle and then spread it. Same thing will be done on this table also. So we have a chamber here, sand will be inside. This will go down every time by one layer thickness and so on. That's a unique feature of this machine. And it also requires different types of coils. And this is the coil we made. So you see this coil in a cathode ray tube. This is the picture tube. Okay. Compared to this coil, we have made it much simpler. That is about the powder bed technology machine. Now I'm going to show you our multi-wire based system. So initial design was a rectangular geometry, and we had wall thickness of something like 30 millimeter. We had a trunnion table. It was going to sit on a scissor. There was an ATC, and then the multiple 4 wires were coming like this. Now, after some more discussions, we realized that it was not necessary. So we went for a dome-like arrangement. Okay, I'll come back to it a little later. Okay, so instead of this, we went for a dome-like arrangement. So this happened because in under the advice of Dr. Ramani, we could do a lot of simplification. This is the original design from BRC, which was 1.3 meter tall. By eliminating a lot of unwanted components, so see the values here, 1.3 meter, 140 kg weight, we could bring down to 400 millimeter height and 40 kg. So by doing it, instead of being a fixed element on top of it, we could make it mobile. So you see on this powder bed machine, I showed the photograph. This gun was sitting on top, whereas in this machine, the gun has actually gone inside. You see, this is the gun. It has gone inside. So then the question came, once we have decided to make a dome, how to introduce a door. So we were exploring whether we should introduce a hinged door or cut it vertically so that it becomes a slidable, or cut it at the bottom or anywhere on the horizontal. Finally, Dr. Ramani suggested cut it like this, because when you cut it like this space is good for human access, and this space is good for the pump, because you saw that the pumps are very tall and they have entry of something like 500 to 550 millimeter hole. Is this a pump? So it had to match with that. So we went for a slant cut, and it had the rubber ring, so we could do it nicely. So this is the ultimate machine. In closed condition, it will be like this, and then this machine will lift off like this. It's a beautiful machine that you can see that it's opening. 2.2 meter in diameter, 4 meter in height. Inside that, we have 4 spools of wire, and 4 wires will go surrounding the electron beam. This is the electron beam gun. So through this, centrally electron beam will come, and then it will create a molten pool into which the wires will go. So this is the machine. This is our multi-wire feeder. We developed for MIG. Same thing is adapted for our EV as well as laser. So you see that there are 4 tubes, and through the nozzle 4 wires will come. The central beam will create a molten pool on the substrate. Wire will dive into the molten pool, get melted. Okay. So I don't know whether there's a video. Yeah, this is the video also. We are able to melt it. This for arc. Same thing we have done for laser as well as electron beam. So still we need to give the finishing touch to the machine. Yeah, I'll come to the conclusion now. So as I told you, electron beam has more advantages than laser, as I listed earlier, in terms of energy efficiency, stress-free matrix, versatility in material and process, low cost. Electron beam machine can be low cost. Not many players are existing today. It's very high, but we have understood the 3V challenges. So our machine cost will be much less. And for all metals in future, we expect EB to dominate, and laser will be limited to ceramics and polymers. And we have already built 2 of these machines, one for powder bed fusion technology and the other for multi-wire cladding. And we also want to go for another machine for sheet metal. We don't have funding, and I'm also not left with much time in IIT, but I will continue the research later. So typically in all my funded projects, I've executed almost 35, 40 crore worth of projects. 25% comes in cash from private companies, and 75% comes from government. And when a private company gives money, they put a lot of pressure so that our product becomes useful to the industry. And that's a very interesting pressure. We enjoy working with them. Okay. And the 50% of the rights of the IP is given to them. and then they will take it up for commercialization. L&T is very serious about commercializing their machine, and we are cooperating with them as much as possible. As I already claimed, we are able to bring down the price of any imported equipment by a tenth, not by 10%, by a tenth. If it is 5 crore, we can make it for 50 lakh. That's a kind of scale we are talking about. By doing a lot of indigenization and innovation. Indigenization means you save on shipping, and foreign country person may not be very loyal to our country, so our prices will be better and things like that. The currency fluctuation, all that is under indigenization. And we are not just going to blindly copy anything. We only get inspired. Okay, we, as I've demonstrated also, we have a number of innovations in our machine, circular table, scissor, Z-axis, spiral spreading like those are, these are all our innovative things. In fact, currently we are looking at, making the complete machine out of battery power, because today batteries have become very powerful. So we are looking at producing a complete EB machine using battery power, because when you take it from the wall plug, because of the high voltage, a lot of fluctuation go to the grid. So we want to minimize that. So we will have a battery based system very soon. So this is what I have to say. So thank you for your patient listening. If you have any questions, we can definitely address. If you want, you can shoot the screen. It has my contact details, email, and all that. Hello? Are you all there? Are there some questions?
Okay, thank you, sir. Dear participants, if anyone have any questions, ask him.
I will copy and paste in the chat box also. Yeah. It's a little hard topic. We are also still learning. But there should be some questions. If absolutely there is no question, then there has been only an overflow. That means I'm a very bad teacher. If you have understood totally without any doubt, then I'm the best teacher in the world. I'm very sure I'm not either. So at least for my satisfaction, ask some questions.
Sir, good evening, sir.
Good evening.
Sir, this is Professor Malleshwar Rao from Ishwar
Yeah.
College of Engineering, Narsaraopeta of Andhra Pradesh.
Okay.
Sir, your presentation is excellent one, sir. But anyway, sir, you compared the EBM with the plasma machining.
Yeah.
Isn't, sir? So actually, sir, which one is better, sir? Plasma, which can be easily controllable.
See, cost becomes a major factor when it comes to private applications. When you talk about DRDO or very high-end industries like L&T, Godrej, their money becomes secondary. Application becomes primary.
Yes,
So
sir. Yes, sir. Yeah.
if you need very precise operation, definitely electron beam is the one you should go for. If your precision is not much, you want to do only joining, then TIG welding or plasma welding, that will be good.
Okay, sir. Okay, sir.
Because the TIG machine, you can get it for about 3 to 4 lakh money.
Okay.
Yeah.
Sir, one more thing, sir. Of course, this is I'm asking about the diesel injection pump.
Diesel?
Injection pump. So
Okay.
that in a compression ignition engine, we are what is that, spraying the diesel is inside.
Right.
Inside the cylinder. So in this one, actually, what I heard that we were using EBM
Okay.
to make to drill the holes, right?
Okay.
Now, is there any other advanced mechanism, sir? Because EBM is the expensive one.
Now the injection point is drilled by EBM, is it?
Yes,
EB.
yes.
Oh, I was
EBM
not
only.
aware. That means it's a good application for us to explore. See, this EB technology, there's no one in the country today, and there are only few people abroad. So they
Okay.
kept the price artificially very high.
Okay.
So see, if you look at a laser, lot of fine tuning is required, calibration is required. In
Yes.
electron beam, you achieve everything by software control.
Okay.
So it need not be very expensive. I showed you the coil geometry. It's a very simple, wound on a bobbin.
Yes, sir.
So electron beam can become very cheap. As I told you, there are three V challenges which are being handled nicely. Thing is, when some people understand it, they keep the price high and then they sell it high.
Okay. Yeah.
Okay, so it's a question of time.
Yes, sir.
So if some industry is using it, then we can definitely develop a machine if they will fund us at a very low price. And see, submarines have double wall like a vestibule in the train. So you open the one wall, transfer something, then evacuate, and then open the other door, double wall system. Similar thing is possible to develop in your vacuum chamber also.
Okay.
So you can have an intermediate transfer chamber into which the parts can be sent in an assembled condition in the fixture. Then it will go back and do the welding and come back. So so you don't have to bust the vacuum every time and then recreate the vacuum. So we can have very simple entry exit methods, good amount of automation. It can be done. It will be nice if you can help us with the right introduction with some of these users of the drilling. What is that? Diesel pump drilling.
Yes, sir. Diesel injection pump. Yeah.
We can definitely work with them. Today, not only diesel, everywhere they are talking about multi-point injection, right? Even petrol engines.
Yes.
So it will find application. That is one. Another application is in all EVs. Today they are using spot welding for connecting the cells together.
Yes. Okay.
Battery manufacturing.
Yes, sir.
Off late, big companies like Tesla have gone for laser. According to me, if they can be successful laser, electron beam will be even more beneficial because everything happens in vacuum.
Okay, sir.
Yeah, but for that application, I'm still in favor of spot welding because spot welding is only one process where exactly at the interface energy gets transferred.
Yes, sir. Yes.
In the form of a nugget. Whereas in laser, you have to go through the top plate, heat the whole thing and then melt and then solidify.
Yes.
So I still love for that application spot welding, but people are moving away from spot welding.
Okay.
Yeah.
Yes, sir. Yes, sir. Thank you, sir. Yeah.
Thank you. Any more?
Sir, this is Madan, Assistant Professor, Complex College of Engineering and Technology, Virudhunagar.
Okay. Madan, okay. Your name sounds familiar. Yeah.
Yeah, we already meeting, so yes, STTP from 2009 to 2023, sir. So very nice section, sir. Actually, I am doing the research in the already I did my PhD, but now I'm focused on the topology optimization, sir. Still,
very good.
Still, openings problem statement is going on in the topology optimization, sir. What is your point of view, sir?
Topology optimization is also lightening to make it light. And today, ANSYS has its own module for it. Most of the, even Autodesk has topology optimization. So that's definitely an interesting area for research. you produce more like a honeycomb-like structure.
Yes, sir.
Isn't it?
Yes, sir. Actually, we are creating our own
and
structure.
Combined with it, they also they have something called generative design. You only give the design constraints where forces are appearing, and then the system iteratively, throws away unwanted material and optimizes it. So topology optimization is certainly a very interesting area of research.
Yes, sir. I think there is a further opportunities available in research side, sir.
Yeah, definitely opportunities are there. See, I listed a few more areas also. Heterogeneous object manufacturing. Similarly, now different layer strategies. All the time we are doing horizontal layer deposition only.
Yes.
Can we not think of different methods of deposition? That's called conformal layers. See, this is a very new technology. 1987 to now, it's less than 40 years, right?
Yes, sir.
Yeah, so there's a lot more. Machining technology or paper technology, it took hundreds of years. Isn't it? Machining technology started at Stone Age. So that the maturity of those technologies is much better, whereas within 30 years, it has given so much of improvement. So I'm very sure. Same with the internet also. Internet, then they talk about so many things, then AIML, a lot of jargons are coming up. And they have influenced in a big way. So these we call as disruptive technologies.
Yes, sir.
So you can use topology optimization only with additive manufacturing, because that only can realize it physically.
But real challenge is mostly we are doing the research in the field of plastic oriented because of the cost. Because go for metal is costly.
Today we have a lot of funds available. We don't get good proposals. Okay. People like you should write proposals vigorously. Proposals will get rejected. For me, right now also my rejection rate is 90%. Okay, 90% of my proposals get rejected.
Okay.
So that means I write so many proposals that I keep getting projects.
Okay.
That is for a professor of IIT Bombay, which is one of the best institutes in the world. So you are in Virudhunagar,
yes,
isn't it? And your
Yes.
infrastructure is not very advanced. So you have to write proposals, form a team, sometimes interdisciplinary or multi-institutional teams. This is what I want to impress upon all of you. You are all faculty members in some colleges. It's FDP program. So write proposals vigorously. You need money for research. Okay, it's like without food you cannot survive. So you need money. Colleges also will be happy when you get money for them.
Of course.
DRDO's fund in a big way. DRDO's, ISRO. ISRO has several divisions. So let's not look at only MHRD or MODROP scheme is there in MHRD for you. AICTE gives you money. But there are many other funding. DRDOs have a lot of funding. They have a lot of interesting problems. So start visiting them. Go to the website, look at them, or if somebody is from DRDO, get connected, go and meet them. Sometimes they do fund your visit. You can request, sir, I want to come and visit in Bangalore at DRDO. They will sometimes fund also because they have money to invite researchers. So look at other funding agencies like DRDO, ISRO, and Army directly has schemes. Navy has schemes. So, but thing is, we are not. You probably are too busy in teaching. You may be teaching 4 courses in a semester. 4 courses too much for me. Okay, I teach only 1 course. Sometimes I cancel my classes. Students are happy. So you're having a lot of teaching work. So you have to balance. When you are young, you will have more courses. As you grow, then you have lesser and lesser courses. Still, 3 courses will be minimum there. That is our fundamental duty. But you have to write vigorously proposals.
Sure.
Yeah.
Okay. Thank you, sir.
Yeah. Welcome. Good luck. Yeah.
Yes, anyone? Any other participants? Any other doubts, queries?
Anything general also is okay.
Yes.
I'm after all much older than all of you. You may need some suggestions. The way Madan asked.
Sir, I think there is no more queries, sir.
Okay, good.
So we sincerely thank you for delivering such an excellent, insightful session in our faculty development program, sir. So in depth of knowledge you shared along with the clarity of your explanation made it outstanding learning experience. And the participants greatly appreciated the way of you connected the theory with the examples and making the session highly encouraged, and it's very impactful. And your contribution has truly enriched to our program, and we look forward the more opportunity to learn in the future. Thank you, sir. Thank you so much.
My pleasure too. Good luck to all of you.
Okay,
Take
sir.
care.
Thank you, sir.
Take care.
Yeah. Yes, sir. Janardhan, sir. Yes, sir. The Senthil Kumar, sir, already joined. So,
Okay, sir. Okay, sir.
yeah.